Okay, so this is the last talk this morning, and Tajima Ryota from Kyushu University, he speak about the p-adic constant for mock modular forms associated to CM forms. Please.
Okay, thank you for introduction. Sorry. Firstly, I am very happy to be able to talk today. And I would like to thank organizers for giving me an opportunity to talk today and to visit ICTS. Thank you. And in this talk, I will explain the p-adic properties of mock modular forms. First, I introduce the history of mock modular forms. Mock modular forms first appeared in Ramanujan's last letter to Hida. However, there is no definition of Ramanujan's mock modular forms in his last letter. There are only some examples and their properties without proof. And let's see this Q series. This Q series FQ and omega Q are examples of Ramanujan's mock modular forms. Okay. And since Ramanujan did not say the definition of mock modular forms, so it is an interesting question to find the suitable definition of mock modular forms. After this, Sander-Tsubegers found the suitable definition of mock modular forms. In 2002, in his postdoc thesis, Tsubegers found that a mock modular form is the holomorphic part of the harmonic mass form. And simply put, harmonic mass form is the harmonic modular form instead of holomorphic. Okay? And because of harmonic property, it is known that every harmonic mass form F naturally decomposes into two parts, the holomorphic part F plus and the non-holomorphic part F minus. And now we define the mock modular form by the holomorphic part of the sum harmonic mass form. Okay? And furthermore, it is known that the non-holomorphic part of the harmonic mass form is sent to the cusp form by the differential operator C. Okay? I will define the later and can you see? CK is this bar is the complex conjugate. Yes, twice. Thank you for question. And next, we look the relation between mock modular forms and cusp forms. It is known that the Xi is surjective map to cusp forms. So therefore, we consider lifts of the cusp form by the differential operator Xi. Okay? And let Z in the Sk gamma 0n, and we only treat the K is in 2n. Okay? We only treat the even natural number weight only. Okay? And then we consider mock modular forms whose non-holomorphic part is sent to Z by Xi. Okay? Let's see this picture. For any mock modular forms F plus corresponds to the non-holomorphic part. And we have the differential operator Xi, surjective map Xi to cusp forms. So therefore, mock modular forms corresponds to cusp form Z. And we call the image of Xi is the shadow of F plus. Okay? And because of surjectivity, so we consider the lifts of the cusp form to mock modular forms. Okay? And we note that this lift is not uniquely determined by Z. There are many Mock modular forms corresponding to Z. Okay? And in most cases, the Fourier coefficients of Mock modular forms are not algebraic. More precisely, if Mock modular form has even integer weight, then their Fourier coefficients are not algebraic in general. And our lift of cusp forms always has even integer weight. Okay? And however, if G is a normalized new form, then there exist Mock modular forms satisfying some algebraic properties. And we call them good lift of Z. Okay? And we also note that good lift of Z is not unique. Okay? For example, if G has complex multiplication, then all Fourier coefficients of the good lift are algebraic. Okay. Okay, let's see an example of good lift. Let Gz be the eta 3z power 8. And this is a unique normalized new form in S4 gamma 09. And it is known that Gz has complex multiplication by Q skewed to minus 3. Then this Q series F plus Q is an example of the good lift of Z. And we note that these Fourier coefficients are algebraic. Okay. Next, I explain p-adic properties of Mock modular forms. For simplicity, we assume that Z is a normalized new form with complex multiplication by an imaginary quadratic field K. As I mentioned before, in this case, there exists an algebraic lift of Z, and that is called good lift. Okay? And because since all Fourier coefficients of good lifts are algebraic, we could regard this F plus Q as a formal power series defined over Cp. Okay? So therefore, for any p-adic number gamma and for any good lift F plus, we can define Mascara F gamma like this. And where epsilon ZVP is the Hida integral of ZVP. Okay. This is a formal power series defined over Cp. In most cases, this Mascara F gamma is just a formal power series, does not have any geometric meaning. However, it is known that there exists exactly one p-adic number alpha Z, such that Mascara F alpha Z is equal to the Fourier expansion of the p-adic modular form. Let's see this picture again. First, we take the normalized new form with Cm by K. Then there exists good lifts whose all Fourier coefficients of algebraic. And because of algebraicity, we could regard this Mock modular form as a formal power series defined over Cp. And for any p-adic number gamma, we define Mascara F gamma like this. In most cases, this Mascara F gamma is just a formal power series. However, there exists exactly one p-adic number alpha Z, depends only Z, such that Mascara F alpha Z is equal to p-adic modular forms. Okay. And furthermore, Candelori and Castella showed this Mascara F alpha Z is over-convergent modular form. And it is known that this p-adic number alpha Z is given by this p-adic limit, where beta and beta prime is the roots of the Hecke polynomial of Z, and capital D is the Euler differential. Okay? And I think this alpha Z is a clue to develop a p-adic theory of Mock modular forms. So therefore, I investigate this p-adic number alpha Z. Okay. And next, we introduce known results about alpha z. In 2012, Brinkman, Gale, Choi, and Kane showed this theorem. Let n be a natural number, and p be a prime number does not divide to n, and z in sk gamma 0 n with Cm by k. If p is split in k, then alpha z is equal to 0. On the other hand, in 2023, the speaker showed this theorem. NPG is the same in the previous theorem. And if p is inert in k, and if the dimension of sk gamma 0 n is equal to 1, then alpha z is p-adic unit. It is unknown. Unknown. And あれ、どこまで喋った？sorry. I say Japanese. Sorry. So, and the assumption of dimension is very, very strong. So, I would like to eliminate this assumption. So, and in main theorem, I can eliminate this assumption in the case G has weight 2 and rational integer coefficient. Okay, so in shortly, we know the split case, but we don't know much about alpha z in the inert case. Okay. We introduce the modular parameterization to describe main theorem. First, we fix a cusp form z in S2 gamma 0 n z. This means the Fourier coefficients of z at infinity are in rational integers. Then we can define the period lattice of z by this period integral. Okay, and we define the modular parameterization phi from the modular curve x0n to c over lambda, defined by this integral. Okay. And we denote the degree of this modular parameterization by capital CZ. And it is known that C over lambda is an elliptic curve. And we choose a YL stress model of C over lambda, this easy y square equal 4x cubed minus da 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 da. And we note that this YL stress model is defined over rational numbers. Okay. And now I introduce main theorem. Let n be a natural number, and p is the prime number more than or equal to 5. And g is in S2 gamma 0 and z, and with Cm by k. Furthermore, we assume that EZ has good reduction at p. I showed if p is inert in k, then Cz times alpha z is a p-adic unit. And we note that Professor Pavel Gale-Choi has obtained the similar result. However, the two proofs were given independently of each other. Okay. And next, I will introduce, I explain rough idea of proof. First, I give the new characterization of the p-adic number alpha z. Let z in S2 gamma 0 z with Cm by k, and f plus is the good lift of z. And p be the prime number that inerts in OK, and p does not divide n. If f plus q minus lambda p epsilon zq minus mu p epsilon zvpq is in zpq tensor qp, then mu p is equal to alpha z. This is a new characterization of alpha z, where epsilon z and epsilon zvp is defined by this formation. Okay. On the other hand, we consider the formal group associated to EZ. Let EZ hat is a formal group of EZ with the parameter t equal minus 2x over y. And we consider the differential form eta defined by x times dx over y. And this has t expansion of the form like this. Okay? And in 2017, Bannai, Kobayashi, Yasuda showed these results. First, let eta 0t is the differential form defined by eta t minus dt over t squared. Then eta 0t is an element, the crystalline homology of EZ hat. And it is known that this crystalline homology has two dimensions, has rank 2, and this basis is omega t and omega star t, where this. Okay, so therefore we could write eta 0t is equal to a omega t plus b omega star t in the crystalline homology. And they showed the coefficient of omega star is a p-adic unit. Okay, so from previous discussion, we have two equations and we investigate the relation between these equations. This is two equations we have. Okay? And first equation lives in the modular curve world. And on the other hand, the second equation lives in the elliptic curve world. So in other words, these equations live in the different worlds. Okay? So we should investigate the difference between these two worlds, and we show that the difference between these equations is equal to the degree of modular parameterization. Okay? So therefore, alpha z is the p-adic valuation of alpha z is equal to the p-adic valuation CZ inverse times B. Okay? And B is p-adic unit. Okay, introduction has finished. And next, I will introduce basic facts to prove main theorem. Okay? First, we define harmonic mass form and Mock modular forms. Let f be a smooth function on the upper half plane H. And if f satisfies these three conditions, then we say that f is harmonic mass form of weight k and label n. First condition is very common condition. F satisfies the modular transformation law for all small gamma in gamma 0 n. And the second condition is very important. Let delta k be the Laplacian, a weight k Laplacian defined by this equation. And we require that f is annihilated by this delta k. And third is cusp condition is similar to the weakly holomorphic modular form, but we omit the details here. And simply put, harmonic mass form is a harmonic modular form. And we denote the vector space of harmonic mass forms of weight k and label n by hk gamma 0 n. And it is known that every harmonic mass form F has naturally decomposed into two parts, two sums, the holomorphic part F plus and the non-holomorphic part F minus. And F plus Z has the Fourier expansion of the form like this. Okay, and we note that when the weight k is equal to 0, then the non-holomorphic part F minus Z has the Fourier expansion of the form like this. And in my talk, we only treat the weight 0 harmonic mass forms. So we only treat this form only. Okay? And this bar is complex conjugation. And furthermore, we define the non-positive part of the holomorphic part is called the principal part of F. Okay? And we define Mock modular form by the holomorphic part of the harmonic mass form. Okay? Next, we introduce two important differential operators. First operator is Xi. In 2004, Burungale and Funk showed this proposition. Let Xw is the 2I power W and del Z bar bar. Okay? Then this Xi gives the map from the harmonic mass form to the cusp forms. And especially they showed that this Xi is surjective map. And we note that Xi2 minus K kills the holomorphic part. In other words, Xi2 minus Kf plus is equal to 0. Okay? Next, another important differential operator is Euler differential capital D. In 2008, Burungale and Rhodes showed this theorem, this proposition. Let D be an Euler differential, then dk minus 1 gives the map from H2 minus k gamma 0 n to the weakly holomorphic modular forms of weight k and label n. And we also note that dk minus 1 kills the non-holomorphic part. In other words, dk minus 1 f minus is equal to 0. Okay, let's see this picture. For all harmonic mass form F, naturally decomposes two parts, F plus and F minus. And we have two differential operators, D and Xi. And the capital D extracts the information of the holomorphic part. And the differential operator Xi extracts the information of the non-holomorphic part. Okay? And furthermore, this Xi is surjective map. Therefore, we could consider the lifts of cusp forms by the harmonic mass forms. Okay. Next, we define good lift of the cusp form. Let G be in Sk gamma 0 n, and F is harmonic mass form of weight 2 minus k. And Fg be the Hecke field of Z. We say that F is good for Z if F satisfies these three conditions. First, the image of F by Xi is equal to Z over the square of the norm of Z. And this norm is P tensor inner norm. And the second condition is that all coefficients of the principal part of F at infinity are in Fz. And we recall the definition of principal part. The principal part is the non-positive part of the holomorphic part. Okay? And the third condition is that the principal parts of F at the other cusps are constant. So, in other words, we require the algebraicity of the non-positive part only. Okay? And we have two results related to good lift. First, let Z be in Sk gamma 0 n and normalizing if Z are normalizing uniform, then there exists a harmonic mass form such that F is good for Z. And furthermore, if G has complex multiplication, Then all Fourier coefficients of F plus are in Heck field Fg. Okay. So we only require the algebraicity of the non-positive part, but if Z has Cm, then all Fourier coefficients are algebraic. Okay. Okay, let's see two examples of good lift. First example is appeared in before slide. This is CM case example. Let Gz is equal to eta 3z power 8. This is a normal uniform in S4 gamma 09. And this is Cm q root minus 3. Then this F plus q is a good lift of Z. Okay. The next example is non-CM case. Let delta z be the Ramanujan delta function in S12 gamma 01. Okay. Then there exists a harmonic mass form F that is good for Z, such that whose the holomorphic part F plus Q satisfies this approximation. Okay. And we note that these Fourier coefficients seems to be transcendental. But it is not proved. But it seems not algebraic. Okay. Huh? So I have not read the details, but it is known that the explicit calculation, the good lift of Poincare series. So I think they express delta z or zz by the Poincare series, and they use the good lift of Poincare series in order to calculate. Maybe. Thank you. Next, we introduce the p-adic properties of Mock modular forms. Let G in Sk gamma 0n with Cm by k, and F is good for Z. We define mass-scale F gamma in CPQ by this equation, or any p-adic number gamma, where epsilon ZVPQ is the Euler integral of ZVP. And we note that all coefficients of F plus Q and epsilon ZVPQ are algebraic. Therefore, this mass-scale F gamma is well defined. And let beta and beta prime be the roots of the Heck polynomial of Z. Then, in 2012, Brinkman, Gelchoy, and Ken showed this theorem. Let P be the prime number inert in K, and we denote dk minus F plus is equal to summation of dn qn, where F is good for Z. Then there exists precisely one p-adic number alpha Z in CP such that mass-scale F alpha Z is equal to the Fourier expansion of the p-adic modular form. And furthermore, they showed this alpha Z is given by this p-adic limit. Okay. And next, we introduce the basic facts of formal group theory. Let mass-scale F be the one-dimensional formal group over ZP of height h. And we define two spaces, Z1F and B1F, by this, and where capital F omega is the formal primitive function of omega. Okay? And by using these spaces, we define the crystalline cohomology of mass-scale F, defined by this equation. And we call this quotient space is crystalline in order to emphasize the Frobenius action. Actually, let phi be the Frobenius on the QP double bracket X. Fx maps to Fxp. Then phi acts on the crystalline homology of F by these equations. Okay? So let omega be an invariant differential of Pascal F, and omega star be the P inverse phi omega. Then we have two results. First, the crystalline homology of F is the free GP module of rank height. Okay? And second, omega star dots phi h minus omega star is the basis of the crystalline homology. Okay? And in my proof, we treat two formal groups. First is Pascal Z. Let epsilon zq be the angular integral of z. Then this epsilon zq is of the Honda type x squared plus p. And this is Eisenstein polynomial. Therefore, by Honda theory, there exists a formal group defined over Zp whose logarithm is equal to epsilon zq. Okay? And next, the another formal group is easy hat. We recall that EZ is the Weierstrass model defined by this equation. And EZ hat is the formal group of EZ with the parameter t equal minus 2x over y. Then this formal group has logarithm log EZ hat, and this logarithm is of the Honda type x squared plus p. Okay? And we note that these logarithms are of same Honda types. Okay? So therefore, by Honda theory, the composite exponential of logarithm gives the isomorphism from Pascal Z to EZ hat over Zp. And therefore, we have the isomorphism from the crystalline homology of EZ hat to the crystalline homology of Pascal Z. And in addition, by straight calculations, we have that h asterisk omega t is equal to invariant differential form of Pascal Z, and h asterisk omega star t is equal to E times ddq epsilon zvbq for some p-adic unit E. This is because h asterisk gives the isomorphism over Zp. Okay. Now, the preparation has finished, and I will prove main theorem from now on. Okay. First, we recall the statement of main theorem. Let n be a natural number, and p be a prime number does not divide n. Sorry. P is the prime number more than or equal to 5, and z is in S2 gamma 0 n z. And z is Cm by k. Furthermore, we assume that EZ has a good reduction at p. If p is inner in k, then Cz times alpha z is the p-adic unit. Okay. First, we give the new characterization of alpha z. Sorry. In 2014, Pavel Gerchoy showed this theorem. Let Z in S2 gamma 0 and Z, and F is good for Z. Then there exists unique p-adic numbers, lambda p and mu p, such that F plus Q minus lambda p epsilon ZQ minus mu p epsilon ZVPQ is in GPQ tensor QP. And I focus on the coefficients of epsilon ZVPQ, and the speaker showed this mu p is equal to alpha z. And Z and F is same as the previous theorem, and P is the prime number inert in OK, and P does not divide N. If F plus Q minus lambda P epsilon ZQ minus mu P epsilon ZVPQ is an element in ZPQ tensor QP, then the coefficient mu P is equal to alpha Z. And I think this is like the p-adic decomposition of F plus Q. So, sorry. Therefore, it is enough to investigate the p-adic decomposition of F plus Q. However, it is not easy to investigate the p-adic properties of Mock modular forms. So, therefore, we investigated the p-adic decomposition YL stress data function instead of Mock modular forms. And next, we introduce the YL stress data function. It is well known that YL stress data function is not lambda periodic. However, we can modify YL stress data function to lambda periodic function. Let Rz be the function defined by this equation, where A lambda is volume lambda, and S lambda is the weight to Eisenstein number. Then, this Rz is a lambda periodic function, where lambda is the period integral of Z. Okay? So because of lambda periodic, we can define R composite phi, and this n tau is function on the modular curve x0n, where phi is the modular parameterization from x0n to C over lambda defined by this integral. Okay? And we can consider the Q expansion of n, and we can separate two parts, n plus Q and n minus Q. And we define the holomorphic part n plus Q by zeta epsilon ZQ minus S lambda epsilon ZQ. And the non-holomorphic part n minus is equal to minus pi over A lambda times epsilon ZQ bar. Okay. And related to this end, in 2014, Haber-Gerchow showed this theorem. First, NQ minus CZFQ is equal to N plus Q minus CZF plus Q. In other words, the non-holomorphic part are cancelled. And moreover, they showed this Q expansion is in GPQ tensor QP for almost all P. And I inspired this theorem, and I showed this Q series is in GPQ tensor QP for all inert prime does not divide N. Okay? And thanks to this theorem, we investigate the p-adic decomposition with a YL stress data function instead of Mock modular form F plus Q. Okay? And first, we show the cancellating of non-holomorphic part. It is easy. It is shown by the straight calculation. And from the definition of good drift, we have the Fourier expansion of the non-holomorphic part F minus Q like this. This is by the definition of good drift. And by the definition N minus Q has a Q expansion like this. Therefore, N minus Q minus CZF minus Q is equal to this. And it is known that the square of the norm of Z is equal to CZ times A lambda over 4 pi square. And by using this equality, we conclude that this is equal to 0. Okay? Therefore, the non-holomorphic part is cancellated. Next, we show the boundedness of p-adic valuation. And we need this lemma to prove the boundedness of p-adic valuation. The radius of convergence of the non-principal part of n plus q minus CZF plus q is at least 1. It is sufficient to show that the image of D is in GPQ tensor QP. Firstly, we treat Dn plus q. By the definition of n plus q, Dn plus q is equal to minus p epsilon zq times zq minus s lambda zq. It is well known that zq has bounded denominators, and furthermore, we can show this pair is GPQ tensor QP by easy consequence, but I will omit the details here. Okay? And therefore, it remains to show that df plus q is in GPQ tensor QP. So we recall two results about the good drift. First, capital D gives the map from harmonic mass form to the weakly holomorphic modular forms. And if Z has Cn, then all Fourier coefficients of F plus are in Fz. By these two results, we conclude that df plus q is a weakly holomorphic modular forms whose Fourier coefficients in rational numbers. Okay, therefore, we conclude that df plus q is in GPQ tensor QP. So we have finished the proof of this lemma. Okay? And it is known that n plus q minus CZF plus q is a gamma 0 n invariant meromorphic function, and whose pole satisfies the algebraicity property. Therefore, let K be this number field. There exists a monic polynomial Gx such that delta power mq times ZJQ times n plus q minus CJF plus q is in Sk gamma 0 n K. Therefore, this Q series has bounded denominators. So there exists a natural number K1 such that pi K1 times is in OK double bracket Q, such that not all coefficients in pi OK. And we recall the Weierstrass preparation theorem. Let HQ in the OK double bracket Q such that not all coefficients in pi OK. Then there exists the monic polynomial in pi OK Q and the unit UQ such that HQ is equal to PQ times UQ. And we call this PQ distinguished polynomial. And we apply this theorem to this Q series. And we have that there exists a distinguished polynomial PQ and a unit U1Q such that the left hand side equal to PQ times U1Q. Similarly, we apply the Weierstrass preparation theorem to these equations. We have that there exists a distinguished polynomial HQ co-prime to PQ, and U2Q is a unit such that the left hand side is equal to HQ times U2Q. And by using these two equations, we conclude that n plus q minus CZF plus q is equal to pi times q times PQ over HQ times units. Okay? And by lemma 1, the convergence radius of left hand side is at least 1. And if HQ has non-zero root alpha, then the convergence radius of right hand side is equal to the minimum of the p-adic absolute values of roots of HQ. And this is less than 1 because HQ is a monic polynomial in pi OK Q. This is contradiction. So we conclude that HQ has no non-zero root And therefore, n plus q minus CZF plus q has bounded denominators. Okay? And now we return to the formal group theory. We recall EZ is the wireless model defined by this equation, and EZ hat is the formal group of EZ with the parameter t equal minus 2x over y. And let eta is the differential form defined by x times dx over y. And this has t expansion of the form like this. And we recall the theorem proved by Bandai-Kobayashi-Yasuda. First, let eta 0t is the differential form defined by eta t minus dt over t square. Then, eta 0t is an element in the crystalline homology of EZ hat. And as I mentioned before, the crystalline homology has a basis of omega t and omega star t. Therefore, we can write eta 0t is equal to a omega t plus b omega star t in the crystalline homology of EZ hat over ZP. And they showed the coefficient of omega star t is a p-adic unit. It remains many times. And by Honda theory, we have the isomorphism from the crystalline homology of EZ hat to the crystalline homology of Pascal Z. And we adapt this H asterisk to eta 0t. Then we have these equations in H1 Chris Pascal Z over ZP. And because H asterisk has the matrix form 1, 0, 0, E for some p-adic unit E. And this is because H asterisk eta 0t is equal to ddq minus zeta lambda epsilon dq minus HQ inverse. This is because the easy straight calculation. Okay? And by using these equations, we conclude that zeta epsilon zq plus a epsilon zq plus eb ez epsilon dvbq is an element in ZPQ tensor QP because HQ gives isomorphism. Therefore, HQ is invertible in ZP double bracket Q. Okay. On the other hand, we have that n plus q minus CZ plus q is equal to zeta epsilon zq minus s lambda epsilon zq minus CZF plus q. And this QC is in ZPQ tensor QP. Therefore, we have that F plus Q plus CZ inverse da 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 epsilon ZQ plus CZ inverse EB times epsilon ZVBQ is an element in ZPQ tensor QP. And we recall the characterization of alpha Z. Z in S2, let Z in S2 gamma 0 n in Z, whose coefficient in Z, and F is good for Z. And P is the prime number that inerts in OK and does not divide F. Then, if F plus Q minus lambda P epsilon ZQ minus mu P epsilon ZVBQ is in ZPQ tensor QP, then mu P is equal to alpha Z. So therefore, thanks to this proposition, we have that CZ inverse EB is equal to alpha Z. Therefore, we have CZ times alpha Z is equal to minus EB, and this is p-adic unit. It remains very many times, but I have finished the proof. And so sorry, I have last slide. In this talk, we only treat the weight 2 new forms. However, we have one example, examples where alpha Z is a p-adic unit in higher weight case. Okay, I will explain this example. Let and the speaker showed in 2013 if G has complex multiplication by K, and if P is inert in K and the dimension of SK gamma 0 n is equal to 1, then alpha Z is a p-adic unit. And S4 gamma 09 satisfies this assumption. In other words, the dimension of S4 gamma 09 is 1. Okay? And let Gz be the eta 3z power 8. Then this is a unique normalized new form in S4 gamma 09 and has Cm by Q root minus 3. Therefore, we can apply this theorem to this Gz, and we have that if P is inert in Q root minus 3, then alpha Z is p-adic unit. So therefore, I would like to determine the p-adic valuation of alpha Z in arbitrary weight case. This is my future work, and I will try hard to do this work. Okay, so sorry, it remains many times, but I have finished my talk. Thank you very much for listening.
Any question or comment?
You have infinite parties of two different G's, which are congruent. Do you expect the alpha G's to be congruent?
Sorry, please more slowly. Okay.
Take two modular form, CM form, and G prime.
Yes.
Which are congruent modulo P.
I have not considered, but so sorry, I have not answered.
I guess that in his case, the modular form has to be coefficient, integer coefficient, rational integer coefficient. And this kind of congruence between rational integer coefficients are very small, 2, 3 kind of thing.
No, but you can take
different weight. Different weight you can have, sure.
Yes.
All the coefficients were algebraic.
Yes.
What sense do you mean that most mock modular forms will go to the mark?
Yes. But we can modify the Fourier coefficients of mock modular forms algebraic in general. So, so if G has not Cm, then the Fourier coefficients are not algebraic in general. But do you see? Can you see? This is non-CM new form, and we have not Q, not G. Then this F plus Q is not in Q bar double bracket Q in general, but F plus Q minus A plus 1 epsilon ZQ has algebraic Fourier coefficients. So therefore, we have similar result non-CM case we adapt instead of f plus q, this algebraic modified.
P-image f plus, then you had some example
Mm.
the P-image and you said all these quotients look transcendental, but you didn't know. But I just wanted to ask if you know that at least one of those Fourier quotients are transcendental.
Eh,
So for the Ramanujan delta function,
Mm.
one of the slides you had an example of a P-image f plus.
this?
Yeah. Comment that some of these quotients transcendental. Yes, that maybe they are. But my question is, do you know, for example, that at least one of the quotients are definitely transcendental?
Maybe there is no explicit example. So it is hard to prove transcendental. So, but we predict that the good drift is algebraic if and only if Z has CF.
Any other question? Okay, so let's thank speaker again.